This first video is meant to clear up some misconceptions that were talked about in last class period on Wednesday. And so I'm going to be discussing mostly old material regarding to Helmholtz free energy, Gibbs free energy. So this is just kind of a review. Hopefully this clears some things up. So the following equations are always true. You always have this equation for Helmholtz free energy, where it's the internal energy minus the temperature times the entropy of the system. And you always will have this equation for Gibbs free energy, where it's the enthalpy minus the temperature times the entropy of the system. Now I'm going to go ahead and talk about special cases of both these equations and how those are useful for us in trying to figure out what's going on in our system. So the first thing to do is Helmholtz free energy is not particularly useful by itself. So what we're going to do is we're going to take a change, and we're going to take the change in Helmholtz free energy at constant temperature. So I'm going to break that up at constant temperature. We can write the change in Helmholtz free energy is equal to the change in internal energy minus temperature times the change in entropy of the system. Okay, so we can use this to calculate out what our change in Helmholtz free energy is. Now, if we're talking about a system that is at constant volume and constant temperature, so constant volume and temperature, that is when we can start discussing whether or not the process is spontaneous or not. So for instance, if we have a Helmholtz free energy that is less than 0 at constant volume and at constant temperature, this is a spontaneous process. Another way you can think about this is the process is going to occur such that you minimize your Helmholtz free energy. Okay, so this might not be clear on why that this is the case. So I'm going to go through a little bit of a derivation to show that this is true. So taking a look at this first equation here, the change, I can write this by dividing everything by temperature. So I'm going to have Helmholtz free energy change divided by T, my internal energy divided by T, and now I'm just left with my change in the entropy of the system. So next I'm going to fill in an expression for delta U. So if we're looking at constant volume, then we can say the change in internal energy is equal to QV, where this is the heat of the system. So we will write that. Then we can say that this is equal to negative heat of the surroundings. So this is the heat transfer in or out of the system, and then it's equal and opposite to the heat transfer in or out of the surroundings. So plugging all this in, what we get is the negative heat of our surroundings over T minus the entropy change of our system. And that's all equal to the change in Helmholtz free energy over temperature. Now, if we write this out, this is equal to the negative entropy of our surroundings. You may recall that from previous lectures. This, we've always discussed this as the change in entropy of our system. And we still have this left-hand side the same. Well, if we factor our negative sign, we can see that this is really equal to the negative change in the entropy of everything. And this is still equal to the Helmholtz free energy change over temperature. So what that suggests is that in order for a spontaneous process to occur, we know that our total entropy change has got to be greater than 0. Based on this equation here, that would mean that our change in our Helmholtz free energy over temperature must be less than 0 because of this negative sign here. Since temperature is always positive, it means that our change in Helmholtz free energy at constant volume, at constant temperature, must be less than 0. Okay. So now we're going to do the same type of discussion of our Gibbs free energy. So our Gibbs free energy here at constant temperature can be written out as a change in G, which is equal to the change in our enthalpy of our system minus temperature times the change in entropy of our system. Now, this at constant pressure is starting to give us information about the spontaneity of our system. So, at constant pressure and inherently constant temperature, our delta G is less than 0 for a spontaneous process. Okay? So that's only true if we're at constant pressure and constant temperature. Now, we can do a similar derivation to show why that is. So, starting off with this equation here, I'm going to do the same math. I'm going to divide everything by temperature. So I have my Gibbs free energy change over temperature. I have my enthalpy of my system over temperature. And now I have just my negative entropy change of the system. Just like before, I'm going to use the idea that at constant pressure, my enthalpy change is equal to QP, which is the heat of my system at constant pressure, which is equal to negative heat of my surroundings. So plugging that in, I have the negative heat of my surroundings over temperature minus the entropy change of my system, and this is still equal to the change in Gibbs free energy over temperature. Once again, this is the same thing as saying the entropy, negative entropy of our surrounding change, negative entropy change of our surroundings, and subtracting off the entropy change of our system is equal to delta G over T. Once again, this is equal to the negative of the total entropy change. Following a similar logic, we know that the entropy change of everything has got to be greater than 0 for a spontaneous process. Thus, our change in Gibbs free energy over temperature has got to be less than 0 because of this negative sign. So this would show us that not only the relationship between the total entropy change and our Gibbs free energy change, but also derives and shows that the relationship with this inequality. Once again, this is only valid for constant pressure and constant temperature. So to reiterate, this is always true. These two equations are always true. These two equations here and here are true at constant temperature. Being able to talk about spontaneity only happens when we talk about specific systems in which we have constant volume in terms of the Helmholtz free energy or constant pressure for the Gibbs free energy. So this hopefully will clear some things up in terms of the free energy state functions that we just discussed.